In the last chapter, we learned the basics of preparing our text to build a model. We learned how to remove punctuation, tokenize, and remove stop words to provide a clean list of words to Python. In this chapter, we're going to learn how to take our cleaning one step further to provide the model with better information for classifying the text. We'll introduce the concepts of stemming and lemmatizing in this chapter. Let's start with stemming. So what is stemming? The formal definition of stemming is the process of reducing inflected or derived words to their word stem or root. More simply put, the process of stemming means often crudely chopping off the end of a word to leave only the base. So this means taking words with various suffixes and condensing them under the same root word. Recall when we removed stop words, it was to reduce the number of words Python has to look at or consider. Stemming is shooting for the same goal by reducing variations of the same root word. If that doesn't make sense, let's jump into examples to see what it means in practice. So here's a collection of sets of 2 or 3 words. The words in each set have similar meaning. So stemming and stemmed are 2 distinctly different words, and Python will not inherently know that these are even related. What a stemmer will do is it'll reduce stemming and stemmed down to their base word of stem. So now, if stemming and stemmed are both represented by stem, we retain the semantic meaning of both words, and now Python views them as the same. Similarly, for electricity and electrical, they're pared down to electric. Berries and berry is interesting because it's more than just cutting off the end of it like we've seen previously. The stemmer will chop those both down to berry with an I. Lastly, connection, connected, and connective will all be chopped down to connect. So this seems pretty useful, but stemming uses very crude rules, so it isn't perfect. For instance, look at meaning and meanness. These words aren't really all that closely related, but they'll be both stripped down to a base of mean, and thus Python will think that meanness and meaning are the same exact thing. So stemmers are correct in most cases, but the trade-off with these simple rules is that it won't always be right. So this all seems interesting, but why do we really care about this? Why does this actually help us for model building? Well, if Python sees grew, grow, and growing as 3 separate things, that means it has to keep those 3 separate words in memory. Imagine every variation of every root word. Maybe we have 1,000 root words, but in our corpus, we have 2,000 total words with every suffix added to the root words. The alternative in this grow, grew, and growing example is applying the stemmer, and now it only has to know what grow means, as each variation of grow is replaced simply by grow. So Python has to look at a lot more tokens without a stemmer, and it doesn't know that these separate tokens are even related. So the benefits of a stemmer is it reduces the corpus of words the model is exposed to, so it's just grow instead of grew, grow, and growing, and it explicitly correlates words with similar meaning. So Python could learn through the training process that we'll discuss later that grow, grew, and growing are similar in meaning, but it also may not, depends on a lot of different factors. In this case, we're not leaving it up to Python. We're being explicit by replacing similar words with just one common root word. There are a number of different types of stemmers that use various algorithms and methods to generate the stemmed version of words. A few that are included in the NLTK package are the Porter stemmer, the Snowball stemmer, the Lancaster stemmer, and a regex-based stemmer. We'll be focusing this lesson on the most popular stemmer in this list, the Porter stemmer. We'll learn how to use the Porter stemmer in the next lesson.